Hi, my name is Elizabeth Russell, and this is my Lab 3 presentation. In this lab, I explored how gravity affects motion by simulating orbits with code. There were two main parts of this experiment. First, I used a star's orbit to figure out the mass of a black hole, and second, I tried to make a spaceship move in a figure-8 orbit around a planet and its moon without crashing. So the purpose of this lab was to connect what we learn about gravity with what actually happens when you model it using code. So for part 1, I looked at the orbit of a star to calculate the mass of a black hole using Newton's law and the gravitational force equation. Then in part 2, I used the same ideas to figure out how fast a spaceship would need to move to stay in a stable orbit without crashing into the planet or its moon. This whole idea was just to see how physics works in real life and in space. So some of the physics principles I used was the momentum principle, which says the net force equals the rate of change of momentum, or basically force changes motion. Then there was Newton's second law, which connects force, mass, and acceleration. And of course, the law of universal gravitation, which tells us how two objects pull on each other based on their masses and distance. My program also used the position update and velocity update formulas. Those are what move each object forward a tiny step in time during the simulation. And then I also used parallel and perpendicular components to see how the force affected the motion and the direction of motion. So for part 1, for the coding part, I set up each object, like the black hole, the star, the planet, and the moon, with their masses, position, and velocity. Then I had the program calculate the gravitational force between every pair of objects, add up the total net force, and use that to update their motion step by step. In part 1, I have the initial conditions, which I did not change, and then the actual code that changes what it is. So I plugged in the star's orbit information to solve for the mass of the black hole. And then for part 2, we have the initial conditions here on the right, which I also did not change except for the speed, which took a bit of trial and error. I changed it so that it would create this figure-8 orbit. And then over here on the right is just the position, velocity, and parallel and perpendicular components. So for my results, the mass of the black hole came out to about 1.86 times 10 to the 38th kilograms, which is super massive, just like we'd expect for something like that. The simulation showed that the black hole's gravity constantly pulls on the star, bending its motion into a circular orbit. And in the second part, the code showed that the planet and moon orbiting each other while the spaceship weaved around both of them in a figure-8-like path. And then we have the moon's orbital speed, which is about 2.4404 e to the 4th, and the moon's orbital period was about 64 hours. And then some possible errors that could be in here is when I treated all the objects as point masses, which makes the math easier but isn't that realistic. I ignored some forces like air resistance and other forces that might exist in space. And then there's also small, tiny rounding errors that build up over time. And then since I had a bit of trial and error to find the right starting speed, that could be a bit of an error. Even with all that, the results were still pretty accurate. So what does this actually mean? So the net force always points toward the black hole, showing that gravity is what keeps the star in orbit. The rate of change of momentum matches the gravitational pull, which aligns with Newton's second law. In the figure-8 orbit, the spaceship was constantly switching which object had the stronger pull, so its path curved naturally back and forth. So now, what if you wanted to predict the motion of the entire system? What would you need to include in your computational model? So here on the slide, I've included a few things that you would need. But if I wanted to take this project further, I'd make the code include every object's mass, position, and velocity all at once. And that would mean each object affects all the others, not just one or two. I could also try adding new forces, like drag or air resistance, to see how that changes motion. Overall, what these upgrades would do, and these little bits and pieces added, would make it even more realistic and closer to what happens in real space systems. Overall, this lab really helped me see how physics works and gravitational pull in Newton's second law. Okay, thank you.